Assalamu alaikum, myself Salsabil Kassar, and welcome to my video presentation on surface analysis project. Subject is adhesion failure analysis with aluminum substrate. Today I will present a surface analysis investigation focused on adhesion failure in coated aluminum alloy panels used in aerospace applications. Adhesion failure is a serious issue because coatings are applied to protect aluminum from corrosion, wear, and environmental damage. If the coating fails, the component's reliability and lifetime are compromised. The objective and aim of this project was to identify the root cause of coating delamination observed in batch number 45 of aluminum panels. Our hypothesis was that the cleaning process before coating deposition was insufficient, leaving behind chemical residues that prevented proper bonding between the coating and the aluminum surface. To test this hypothesis, we used two advanced surface analysis techniques: X-ray photoelectron spectroscopy and time of flight secondary ion mass spectrometry. Sample description: we analyzed two samples. Sample A that showed good adhesion. This sample was properly cleaned and had not failed. It represents a healthy aluminum surface. Whereas sample B failed because of the bad adhesion. This sample showed coating delamination. The coating was peeled off, exposing the substrate surface. Comparing these two samples allowed us to identify what went wrong. Part 1: XPS analysis quantitative. XPS helps us answer two important questions: which elements are present on the surface and in what chemical form they do exist. Since adhesion depends strongly on surface chemistry, XPS is ideal for this investigation. XPS survey scans results: sample A good adhesion, strong signals from aluminum and oxygen, a small amount of carbon which is normal and unavoidable. This indicates a clean aluminum oxide surface, whereas sample B failed adhesion. Aluminum and oxygen signals are much lower, large increase in carbon and fluorine. This immediately suggests surface contamination. High resolution XPS results. When we looked more closely, sample A showed aluminum oxide and metallic aluminum, a healthy oxide layer needed for strong adhesion. Sample B showed very high carbon content, about 45%, high fluorine content, about 24%. Aluminum signals were very heavily masked. This means the aluminum surface was covered by an unwanted layer. Oxide thickness calculation: using XPS signal ratios and a standard equation, we calculated the oxide thickness. Sample A had an oxide thickness of about 3.25 nanometers. This is normal and ideal for bonding, whereas sample B showed almost no metallic aluminum signals. This means the contamination layer is thicker than 5 nanometer. The coating never touched the aluminum oxide directly. Key XPS conclusions were: sample B is not failing because of poor aluminum quality. The failure is due to thick carbon fluorine contamination layer on the top of oxide. Part 2: ToF SIMS analysis. While XPS tells us what elements are present, ToF SIMS tells us what molecules are present, where they are located on the surface. This is essential to identify the source of contamination. In the failed example, we observed peaks corresponding to CF plus, CF3 plus, and C2F5 plus, a repeating pattern related to CF2 units. This pattern is strong fingerprint of the fluorocarbon polymer such as PTFE, that is Teflon. Fluorinated release agents are lubricants. TOF SIMS chemical mapping. We also created chemical images of the surface. Aluminum map showed patchy exposure. Fluorocarbon map showed high intensity, exactly where delamination occurred. This confirms that delamination is localized at the failure sites. Depth profiling interface analysis. To To understand where the contamination sits, we performed depth profiling using a gas cluster ion beam. What we observed was at the surface, very high carbon and fluorine. At the interface, fluorine drops, aluminum and oxygen increases. In the bulk, stable aluminum signal. Interpretation: the fluorocarbon contamination is a separate layer sitting on the top of aluminum oxide, not mixed into it. The final root cause conclusion: the adhesion failure is caused by a fluorocarbon contamination layer approximately 5 to 8 nanometers thick on the aluminum surface. Evidence: XPS confirmed high fluorine and carbon masking aluminum. ToF SIMS confirmed the contaminant as a fluorinated polymer. Depth profiling showed it as a discrete surface layer. The most likely source is fluorinated release agent or lubricant from the sampling or forming process. Impact on performance: adhesion. Fluorocarbons are not stick materials. The coating cannot wet or bond to the aluminum oxide, result instant delamination. Electrical: if applicable, the layer is insulating, would cause high resistance on open circuits. Recommendations to prevent failure: future review and upgrade the solvent cleaning process. First one, current cleaning is not removing fluorinated residues. The second one is introduce an oxygen plasma cleaning step. Oxygen plasma effectively removes fluorocarbon contaminants that solvents cannot. And the third one is audit upstream processes, especially stamping, molds, and lubricants used before coatings. And in the final takeaway, we can say that the study shows even nanometer scale contamination can cause total coating failure. Surface chemistry is just as important as bulk material properties. Combining XPS and ToF SIMS provide a powerful approach for industrial failure analysis.